So let's start with a question that's fundamental and maybe even a little unsettling. Why, in a universe that we know is just teeming with hundreds of billions of stars, in our galaxy alone, why does it feel so profoundly silent? This is the core issue that famously haunted the physicist Enrico Fermi way back in 1950. It all crystallized into that simple but kind of crushing query: where are they?
It really is the ultimate paradox of cosmology, isn't it? And today we're going to try and move past just the philosophical musings and really dive deep into the technical expectations, the one set by the Soviet scientist Yosef Shklovsky and, most famously, Nikolai Kardashev. Our mission today is to define what a highly advanced galactic civilization, what they actually termed a cosmic miracle, should look like. And then we're going to ruthlessly compare those scientific expectations against the hard, cold facts of astronomical observation.
Right. So we're not just looking for, a little green man or a simple blip of life. We're looking for phenomena that appear, and I'm quoting the source material here, supernatural. Or, to be more specific, we're looking for evidence of engineering and activity so vast that it's just not subject to the predictable, purely deterministic laws of, non-living matter. This isn't just listening for a short burst of sound. It's searching for an organized, a colossal phenomenon that has to be artificial.
Precisely. And that core framework they established is so critical. If we use our most advanced observational tools, our best radio telescopes, our best infrared arrays, and we still observe no such cosmic miracles, no massive engineered structures, no clear manufactured radio signals, well, that raises a very severe and unsettling possibility. It strongly suggests that intelligent life either fails to reach a truly high, resource-intensive level of development, or if it does, it simply doesn't manifest itself on the galactic scale that we're now capable of observing. The stakes couldn't be higher, really. The answer determines the extent of our practical loneliness in the cosmos.
Okay, so let's unpack that concept of development. Because we need a way to measure the scale of these potential cosmic miracles, right? And that's where the technical language provided by Kardashev himself comes in, the Kardashev scale. This is the foundation we need. It's a way of benchmarking civilizations entirely on their control and their consumption of energy. It's just power for power's sake, but extrapolated to the absolute cosmic limit.
It's an incredibly elegant, power-based metric. And it's elegant because it avoids all the pitfalls of, say, trying to define intelligence based on biology or social structure. It anchors us instead to quantifiable physics and observable energy signatures. And we start where we are, roughly.
A Type 1 civilization, this is the planetary master. Their technological level is similar to, maybe just a little bit above, our current capabilities here on Earth. They've achieved total control over the energy resources of their home planet. Their energy consumption is relatively modest on a cosmic scale, around 10 to the power of 20 ergs per second. So they're managing global power grids, weather systems, full resource utilization on their world.
Yeah, and to truly grasp that 10 to the 20 ergs per second figure, you have to think about what Earth is currently using. We're actually close to Type 1 status, maybe 0.7 or 0.8 on the scale, depending on who you ask. But when a civilization actually hits that Type 1 benchmark, they're consuming thousands of times more energy than all of our current human activity combined. But, and this is the key, they're still restricted to a planetary budget.
But then we make the first just massive exponential leap into the realm of true cosmic miracles, a Type 2 civilization. This is exponentially more advanced. They're not just planetary masters. They are stellar masters. They have mastered the entire energy output of their central star.
Yeah, and their consumption just jumps dramatically to about 10 to the power of 33 ergs per second. That is 13 orders of magnitude greater than Type 1.
13 orders of magnitude. That's hard to even imagine.
It is. To put that in perspective, the energy output of our sun is approximately 3.8 times 10 to the 26 watts, or roughly 4 times 10 to the 33 ergs per second. So a Type 2 civilization is literally harvesting every single erg their star produces.
And to do this, they have to engage in megastructure construction. That is, frankly, science fiction to us. This is where the classic illustrative technology comes from, right? The Dyson sphere.
That's right. And the Dyson sphere is often misinterpreted. People think of it as a solid, uninhabitable shell, which is not quite right. In reality, the concept that Shklovsky and Kardashev advanced suggests it could be a dynamic construct, a massive network of orbiting habitats or collectors that fully, or at least partially, surrounds the star to harvest the maximum available energy.
The source material also references something called Evercities. What exactly are we envisioning there?
Well, these are likely complex space habitats or massive floating power stations. They might be using thermonuclear energy derived directly from the outer layers of the star itself, or even utilizing the substance of large unused planets in the system as fuel. The term Ether cities just evokes the enormous quantities of these structures you'd need to capture the entire stellar output. The key takeaway is that Type 2 structures are defined by total, unconstrained control over their star's energy budget. They've achieved energy independence on a stellar level.
And then we reach an incomprehensible apex, a Type 3 civilization. This civilization is not confined to one star system or even a local stellar neighborhood. They are true galactic masters.
They control energy on the scale of their entire galaxy. Their consumption jumps again to approximately 10 to the power of 44 ergs per second. I mean, just imagine a sphere of Dyson structures encompassing every single star within the Milky Way, or maybe highly efficient machines that are tapping into the galactic core's massive energy output. They are literally galactic engineers, commanding an energy output equivalent to hundreds of billions of stars.
So, if we accept this premise that unrestricted technological development will just continue, which seems like a logical assumption for an advanced intelligence, why must it lead to these manifestations on a galactic scale? Why does Type 3 have to be the logical conclusion?
Because of the principle of exponential growth and resource utilization. It's a simple logical progression. If a civilization doesn't destroy itself, it logically continues to seek more efficiency and more capacity. So once you've exhausted the energy of one star, that's Type 2, the only place left to grow is outward, toward the energy of the next star and then the next cluster. Unrestricted development must eventually lead to manifestations on a general galactic scale. If they exist, Type 2s and Type 3s should be, well, they should be physically impossible to miss, precisely because of the scale of the energy they require and consume. Their presence should fundamentally alter the visual and the radio landscape of the entire cosmos.
Okay, so that sets the benchmark. If a Type 2 or a Type 3 civilization has this just colossal energy budget, the next logical question is, how do they use that power to contact unknown civilizations like ours, given the immense distances between stars and galaxies? What's the optimal signaling strategy?
And this is really where Kardashev's genius lay. He didn't approach SETI as a guessing game, but as an engineering problem for a hyper-advanced entity. Now, Freeman Dyson had initially suggested that the sphere itself, the physical apparatus harvesting the energy, would radiate infrared energy, waste heat corresponding to its surface temperature, and that thermal emission could serve as an accidental signal. But Kardashev argued that this is far from the most economical or effective method for communication.
He strongly preferred radio waves. But
Yeah.
hang on, if they have infinite energy, why would they worry about economy? Why does radio win out over infrared?
Radio wins because of bandwidth and modulation capability. Sure, they might have nearly infinite energy, but they still need to maximize information throughput across vast distances. Radio significantly increases the communication range compared to the shorter wavelengths of infrared radiation, and crucially, radio waves are easily modulated. That means they can be encoded with complex, high-density information. It just opens up nearly unlimited possibilities for high-volume information transfer. If you're trying to send the Encyclopedia Galactica across 10,000 light-years, you choose radio.
And since they don't know exactly where we are or who else might be listening, the signal needs to be everywhere at once. This demands the principle of isotropic transmission radiating equally in all directions, essentially creating electromagnetic floodlight.
Exactly. And the source material notes that technically, creating a single, powerful, and perfectly isotropic emitter is physically challenging, even for a Type 3. So the most logical and natural way to achieve this kind of universal broadcast would be to distribute an enormous number of smaller, comparable emitters, maybe across the entire planetary system, or for a Type 3, across a vast stellar cluster. That way, the combined signal uniformly blankets a wide swath of space.
Okay, now let's turn to the really unique philosophical component that Kardashev introduced, which reveals a profound insight into, I guess, galactic sociology, the altruistic imperative. He believed these radio transmissions should be unanswered, or, using the Russian term that's cited in the source, bezotvetny.
Yes, this altruistic behavior is based on a kind of cosmic moral contract. The thinking is, if a super-civilization in its own primitive past received valuable, uncompensated information from its own, more developed cosmic neighbors, and they must have, to reach Type 2 or Type 3, then it incurs a permanent moral obligation to pass that knowledge on to its younger brothers in the universe. without expecting a reply or payment or even an acknowledgement.
That's a profound idea. It's like they recognize that receiving this information was the catalyst for their own success, and that debt can only be repaid by paying it forward to the next generation of life. They just broadcast information purely for the benefit of others, recognizing that the distance and the time involved make a two-way conversation kind of futile anyway.
Right, and this obligation directly influences the technical specifications. If your purpose is maximum knowledge transfer, the signal cannot be a narrow, repetitive sequence like a simple hello.
It has to be an information torrent.
Correct. The signal has to be broadband, covering a wide range of frequencies, and it has to carry a massive amount of information immediately upon detection. Furthermore, to maximize the distance and minimize the power needed for clarity, the signal's spectral characteristics should be close to the inverse of the natural cosmic and quantum noise spectrum.
Okay, that sounds highly technical. If we translate that into common language, what does that actually mean?
It means they should transmit where the universe is quietest. If you look at the natural radio noise spectrum, the background static caused by galactic activity, thermal radiation from gas clouds, and the fundamental quantum limits of the universe, it's shaped like a massive U or a deep valley.
So where is that sweet spot, that cosmic quiet zone?
Well, the natural noise spectrum has a very deep minimum in the decimeter and centimeter wavelength range.
Yeah.
So tens of centimeters down to just centimeters. At low frequencies, you've got thermal noise from the galactic plane and background radiation. At extremely high frequencies, you have quantum noise interfering. The space between them is the optimal valley. Therefore, the primary energy of an artificial signal designed for maximal long-distance information should be concentrated precisely in this specific band.
So an advanced civilization, being rational engineers, would choose the mathematically perfect frequency band to broadcast a colossal library of knowledge. And that choice, centered around the few centimeter wavelengths, becomes a key marker we should be looking for.
Absolutely. The source even references specific spectral curves, like those plotted for sources such as CTA-21, CTA-102, and Virgo A. They show the expected profile of this kind of artificial source. It should drop off linearly at high frequencies and just stand out dramatically against the background noise in that centimeter range. It's the signature of optimal engineering in the cosmos.
Okay, so if these super civilizations are transmitting exactly in the quietest, most efficient frequency band, how far could our current radio techniques theoretically reach to detect them? Let's quantify that detection potential because this defines the whole scope of our search.
The theoretical maximum ranges are truly staggering, and they speak directly to the feasibility of finding them if they actually exist. For a Type 2 civilization using an isotropic omnidirectional signal, that blanket broadcast we talked about, we could theoretically find them up to 10 million light years away.
10 million light years, that distance. That encompasses the entire local group of galaxies. I mean, Andromeda, the Triangulum Galaxy, all of our nearest neighbors. If Type 2s are common, they should be filling our local radio sky.
They should. But there was a technical trade-off here. It's about information content. To achieve that maximum range, the reception band would have to be incredibly narrow, just hundreds of kilohertz. This severely limits the information content, perhaps to only hundreds of thousands of binary units per second. So we'd know they were there, but decoding the Encyclopedia Galactica would take millennia. It's a very low bandwidth signal at maximum range.
Okay. Now, for the Type 3 galactic masters, if they can harness 10 to the 44th ergs per second, what's their theoretical reach?
For a Type 3 civilization, the detection range just leaps to 10 billion light years away. This surpasses the distance to the most remote objects we know of in the entire observable universe. We could detect them in a frequency band of tens of thousands of megahertz, which means the information transfer is vastly higher. A Type 3 civilization should, quite literally, be observable across the entire observable cosmos. We should be seeing their signatures in early universe surveys.
So the engineering goal is to maximize the chance of detection while minimizing the possibility of misidentification. If we pick up a radio source from, say, 5 billion light years away, how do we confirm it's a Type 3 signal, and not just an unusually energetic quasar given that distance? We need robust, objective criteria for distinguishing artificial signals from natural phenomena.
Kardashev proposed 5 key criteria, all based on physics and engineering requirements, for this exact purpose. First, the specific spectrum. We already mentioned the focus on the centimeter range. The specific signature, though, is a mathematically linear decrease in spectral flux density as the frequency increases in the high-frequency range. It should look manufactured, not like the chaotic curved spectrum of, say, a supernova or a pulsar.
Second, small angular sizes. This is critical. For Type 2 civilizations, their transmitting systems, even if they're distributed over a planetary scale, would be tiny relative to the distance. So if they're hundreds of thousands of light years away, they should appear as very small point sources, something on the order of 0.01 to 0.001 arcseconds. If we detect a massive radio source that is physically tiny, that is highly suspicious, it implies extreme energy density in a very small area.
Third is circular polarization. This is a functional necessity for high information transfer across interstellar distances. When radio waves travel through the interstellar medium, which has weak magnetic fields, the rotation of the polarization plane, which is known as the Faraday effect, can severely distort the signal.
So the magnetic fields are essentially twisting the radiolight as it travels, scrambling the information.
Exactly. To protect the signal integrity and prevent this distortion, advanced civilizations would switch from linear polarization to circular polarization. The detection of a strong, circularly polarized broadband signal would be, well, a smoking gun of artificiality.
Okay, and the fourth and fifth are more like observational giveaways. Time variability, a signal that blinks or changes in a non-natural, maybe mathematically coded pattern, and specific spectroscopic quirks.
And the most famous quirk here involves the 21-centimeter hydrogen wavelength. This line is a universal marker of neutral hydrogen. It's a fundamental measurement for mapping the universe. Kardashev predicted that an advanced civilization might deliberately engineer a noticeable feature, such as a sharp cutout, a rectangular absorption band, right near this 21-centimeter line.
Why would they do that?
It acts as an intentional flag. They're essentially saying, we know you look at 21-centimeter hydrogen for your natural measurements, so we are placing a powerful, structured feature right next to that universal benchmark to draw your attention. We are here. It would be a signal that is fundamentally non-natural because it requires intimate knowledge of cosmic physics and a deliberate choice to manipulate the spectrum.
This moves us beyond just listening for a radio signature to actually trying to image these colossal structures. So let's discuss the next phase of detection: cosmic interferometers and radio holography. This is where the visualization of the scope becomes truly staggering.
This is the realm of true Type 2 and Type 3 detection. An interferometer works by combining signals from widely separated telescopes to achieve the resolution of a single telescope the size of the distance between them, the baseline. So to achieve the necessary resolution to resolve planetary-scale structures across space, we need vast baselines.
Okay, so let's consider Type 2 imaging first. What kind of baseline do we need to image a Type 2 civilization in our own galaxy?
We would need a lunar interferometer, a baseline distance from the Earth to the Moon. Operating at a wavelength of about 1 centimeter, we could achieve a resolving power of 5 times 10 to the -6 arcseconds.
That resolution is extraordinary. What can we actually resolve at that power?
Even if that Type 2 civilization is at the opposite end of our own Milky Way, a lunar interferometer could get a crude but reliable image of it. And that image could reveal structures that are undeniably artificial, perhaps vast rotating parallel or perpendicular lines, or a system of concentric circles of transmitters, structures that simply do not coalesce naturally from gas and dust and gravity.
And if we want to image a Type 3 civilization or maybe a Type 2 civilization far outside our galaxy, say in the Virgo cluster of galaxies, tens of millions of light years away,
then we need to increase the baseline again, maybe up to 1 astronomical unit, the distance from the Earth to the Sun. Theoretically, this provides a monstrous resolving power of up to 10 to the -8 arcseconds.
just to put 10 to the -8 arcseconds into perspective for you listening, that's equivalent to seeing a single human red blood cell on the surface of the moon.
Precisely. At this level of resolution, we could image a Type 2 civilization within tens of megaparsecs. We could potentially see engineering in the Virgo cluster, millions of light years away. We'd be looking back in time millions of years, examining the geometric layout of their artificial systems.
And the absolute definitive proof, the holy grail of detection, would be radio holography.
Yes. The concept, which was first suggested by Kardashev and Pereysky, involves using these massive interferometers to obtain three-dimensional images of radio sources. Holography involves capturing phase information, which allows for the reconstruction of depth.
A 3D map of a radio source.
Right. And a 3D image of a radio source would unambiguously and definitively settle the question of artificial versus natural origin. If you reconstructed a Type 2 civilization and it appeared as an engineered disk 40 light years across, rotating with specific power transmission patterns, well, there would be no scientific argument left. If it looks like a star-spanning machine, it is a star-spanning machine.
So we've established that if Types 2 and 3 exist, They should be detectable across just mind-boggling distances using existing or near-future technology. The capabilities are there. But now we have to turn that powerful telescope to the reality of the cosmos. What do the observations actually tell us? Why haven't we found any local Type 2 civilizations?
Well, the silence is more than just deafening. It's statistically significant. The lack of observation is in itself a powerful piece of evidence. Let's start with the definitive test that we can conduct with current radio astronomy, the Andromeda test, M31.
Right, M31 is our neighboring giant spiral galaxy, the largest in the local group containing hundreds of billions of stars, a perfect place for Type 2s to proliferate.
And if they have, they should be acting logically. They should reasonably assume that intelligent life might be around our sun and perhaps directing powerful signals our way. They should be, as the Torus says, holding our galaxy in their radio lobe, directing powerful centimeter-range signals toward us, the optimal broadcast frequency we just discussed.
And what were the results of that search?
Observations of M31 show a distinct lack of powerful artificial sources. The known radio sources there do not exceed 1/10 the power of the natural galactic source Cassiopeia A. And Cassiopeia A, for context, is a remnant of a massive supernova explosion in our own galaxy. It's one of the brightest natural radio sources in our sky.
So, if Type 2 civilizations exist in Andromeda and are aiming signals toward us in the centimeter range, their power is at least 1,000 times less than the sun's total power. That is a stunningly low power output for a civilization that has the capability and energy budget to harness the total output of a star.
It forces us into a binary conclusion. Either Type 2s are extremely rare, or they're operating far below their theoretical energy capacity, using highly inefficient methods, or maybe methods we just haven't predicted.
What about the alternative strategy? Maybe they aren't using an isotropic blanket signal. Maybe they're saving power by using a focused directional beacon, an artificial lighthouse rotating across the galaxy. This would look like an engineered pulsar.
This is a highly probable strategy for localized contact. The design would likely be a narrow, knife-like beam, perhaps 5 degrees wide by only 0.1 degrees tall, rotating slowly, maybe with a period of several days, in the plane of the galaxy. This rotation ensures that a substantial portion of the galaxy's star systems pass through the powerful beam over time.
And if such a lighthouse were operating within our galaxy, say 10 kiloparsecs away, how powerful would it need to be for us to detect it?
Even with that directional beaming, the source material indicates its power would still need to be 1,000,000 times less than the sun's total output to be detected by our current limits. And while that is still significant energy, modern radio astronomy is constantly lowering this detection threshold, and yet, no such artificial lighthouse has been confirmed. Every single signal that looks like a pulse beacon has eventually been confirmed as a natural phenomenon, usually a fast-spinning neutron star.
Okay, and what about the infrared search? Looking for those massive accidental signatures of Dyson spheres. If a Type 2 civilization builds an artificial biosphere around its star, using up the full energy supply, it must inevitably radiate waste heat or infrared energy corresponding to its preferred surface temperature.
And that preferred surface temperature is typically estimated to be around 300 Kelvin, which is close to Earth's average surface temperature of 27 degrees Celsius. Such a structure should be visible to us as a powerful, non-stellar point source of IR energy. But while infrared astronomy has dramatically matured and many strong IR sources have been found, they have all, without exception, been confirmed as natural phenomena. Things like protoplanets forming, dusty shells around young stars, or interstellar molecular clouds. No definitive Dyson sphere candidate has emerged.
This overwhelming pattern of initial suspicion followed by natural confirmation brings us back to a really crucial guiding philosophical principle that Shklovsky proposed, the presumption of naturalness.
It's the necessary methodological rigor for this field. You absolutely must have it. We have to strictly apply the presumption that any cosmic signal or phenomenon, no matter how unusual or exotic it seems, is natural until conclusive, objective proof of artificiality is obtained. The history of astronomy supports this. I mean, when pulsars were discovered, they were initially dubbed LGM for little green men because their regularity seemed utterly artificial. They were later proven to be natural, rapidly rotating, magnetized neutron stars. And Shklovsky argues that other apparent cosmic quasi-miracles will likely follow the exact same trajectory.
So based on the current data, what is the hard, cold conclusion regarding our immediate cosmic neighborhood?
Modern astronomical observations, including that M31 test, strongly suggest that Type 2 civilizations are absent in our galaxy and in M31. The limits are so tight in the centimeter range that we can state this with a very high degree of confidence.
And what about Type 3? Are we capable of ruling them out yet?
Type 3 civilizations are much harder to rule out conclusively without widespread, ultra-deep interferometric studies, like that 1 AU baseline we discussed. However, the initial enthusiasm that surrounded specific extragalactic radio sources in the 1960s, like CTA-102 and CTA-21, where Kardashev initially theorized they might be Type 3 candidates, well, that faded very quickly. They were all revealed to be quasars, extremely powerful, but ultimately natural galactic cores powered by supermassive black holes. The largest candidates for artificiality have always failed the test of the presumption of naturalness.
The observational evidence points overwhelmingly toward absence in our local volume, which brings us right back to the heart of the issue, the Fermi paradox. The lack of concrete evidence, the lack of visitors over the past 4.5 billion years of Earth's existence, it just flies in the face of the Copernican principle, which suggests we are nothing special and that life should be common.
It does. If the universe is full of life that inevitably becomes expansive, then someone should have mastered interstellar travel and colonization long ago. Their presence should be ubiquitous, filling the spiral arms of every galaxy. And since the radio sky is silent and the infrared sky is equally quiet, we have to revisit the possible scenarios for why they are absent.
The source outlines three main categories of resolution for the paradox, assuming the absence of visitors is genuine. Let's start with the practical and economic limitations.
This resolution suggests that interstellar travel is simply too costly in energy and resources for massive resettlement or colonization drives. And while reaching Type 2 implies colossal power, the sheer scale of the colonization effort required to fill a galaxy might still be economically prohibitive, or, more accurately, cybernetically unprofitable. Therefore, only automated probes are used, strictly for scientific research, and perhaps they just haven't reached us yet or we haven't recognized them.
Okay, the second scenario accepts the feasibility of interstellar travel, but suggests that the colonization wave is delayed.
This is a timing issue. The wave of expansion may be propagating very, very slowly across the galaxy. Alternatively, perhaps the whole process of colonization started relatively late in galactic history. Or, and this is the most interesting part, the colonization may have started simultaneously across the galaxy, resulting in vast empires of influence. And we just happen to be located on an uninhabited border zone between two established spheres of influence. We're in a galactic no man's land waiting to be claimed.
And the third, the most ethically complex possibility, the one that appeals to our sense of cosmic drama, galactic ethics, or the zoo hypothesis, the quarantine.
This posits that the galaxy was in fact colonized long ago, perhaps billions of years ago. But the resulting supercivilization refrains from revealing itself to avoid influencing our primitive life. Galactic ethics demand that we be allowed to solve our own fundamental crises, overpopulation, nuclear war, environmental ruin, without external overwhelming technological interference. We are, in effect, a protected nature reserve, a planet-sized ethnographic museum under strict observation.
So whether the explanation is prohibitive cost, unfortunate timing, or an ethical quarantine, the overall set of facts forces us toward what the sources call an unconsoling conclusion. Type 2 and Type 3 civilizations are, at the very least, absent in the local group of galaxies.
And the implication of that is profound. It means Earth-type civilizations must be either extremely rare or virtually absent in the local group. If some primitive life must eventually become expansive, if that drive to increase energy and complexity is universal, then the initial rarity of life is the primary explanation for the silence.
But there is a powerful alternative to the idea of rarity that we have to integrate fully here. What if advanced life simply decides expansion is a failed strategy, the golden age strategy?
This is a fascinating counter-argument to the Type 3 assumption that size equals success. This strategy posits that advanced civilizations achieve a kind of equilibrium or golden age, where they realize that physical expansion is ultimately cybernetically unprofitable.
Okay, what does cybernetically unprofitable mean in this context?
It means that as you expand physically across space, the speed of information exchange, which is limited by the speed of light, slows down relative to the size of your civilization. If a Type 3 civilization spans 100,000 light years, a complete loop of information exchange takes 100,000 years. This makes coherent decision-making and real-time governance impossible. They become too slow to think.
So the most advanced civilizations realize that the true measure of success isn't physical size or energy harvest, but maximizing information density and speed of thought. They choose to turn inward.
Precisely. They focus on internal complexity and development, maximizing the number of computations per second within the smallest possible, most compact structure. perhaps miniaturizing into non-observable cybernetic habitats near their home star. The source material notes that this possibility is practically equivalent to our loneliness, because intelligence would become a multi-connected manifold.
Let's clarify that term for the listener. A multi-connected manifold.
It's a collection of separate, completely isolated pockets of intelligence that never interact. If civilizations reach this golden age state of extreme, self-contained, information-maximizing compactness, they effectively take themselves out of the cosmic game of expansion. Their existence would be functionally irrelevant to us, making our isolation practical, even if they were common elsewhere.
To structure these possibilities, the sources provide a detailed look at 6 possible long-term fates for extraterrestrial civilizations, along with subjective probabilities assigned by the authors. Let's review the scenarios where contact, or at least unification, is achieved.
Scenarios 1, 2, and 3 all focus on unification strategies over massive timescales, between 1 and 10 billion years. Scenario 1, with its 60% subjective probability, is unification into a single, compact cosmic object. This leads to a quick burst of final development and preparation for joining the ultimate supercivilization. Scenarios 2 with 20% and 3 with 10% describe similar processes, but focused on unification within large clusters or very large clusters of galaxies rather than a single compact object. These are seen as the most likely paths for successful long-term survival. And what happens to a developing civilization like ours, the younger brothers, after contact in these successful scenarios? What's the predicted fate for us? The common outcome is the same: rapid technological, social, and economic change, leading to integration or unification with the supercivilization. And the rather amusing prediction, which underscores the profound technological gap, is the organization of an ethnographic museum on Earth.
We're definitely the museum piece. The visitors would study our primitive self-destructive phase before we were assimilated. That puts a humorous, yet kind of depressing spin on the zoo hypothesis.
It does. Then we have the statistical outlier scenarios. Scenario 5, with an 8% subjective probability, is self-destruction before contact. These are the civilizations that failed to overcome their internal crises: nuclear war, resource depletion, and so on. This means we might only find remnants or traces of these failed civilizations near stars.
And what about the idea that we're simply the first?
That's scenario 6, with a 1% probability. This requires us to assume that the 4 billion years it took for life to develop here is an unusually fast timeline. While contact is possible later, under any of the other scenarios, for now, we're unique. Finally, scenario 4, at 1%, where full galactic colonization has occurred, but we simply lack the data to detect it, which is becoming increasingly unlikely based on the observational limits we've been discussing.
We stand at a profound conclusion. The observational evidence and the engineering logic suggest practical solitude. But before we accept this, we have to address the danger of extrapolation. We're trying to apply our current limited understanding of civilization and technology to systems that are potentially far beyond our comprehension.
The sources offer a brilliant historical warning against this type of Earth-centric thinking. Think about the great 17th century physicist Christian Huygens. He was a pioneer, yet he was constrained by the technology and philosophy of his era. He took the known astronomical fact that Jupiter had moons, and he combined it with the astrological prejudice of his day, the belief that the moon patronizes sailors.
And what was his grand conclusion based on this extrapolation?
Huygens concluded that Jupiter's surface must be seeded with hemp, which was necessary for making rigging and sails for the dominant sailing technology of his time. He reasoned that if they have moons, they must have sailors, and sailors need hemp. It just shows the folly of basing cosmic conclusions on transient, Earth-specific technology or social constructs. We may be making our own equivalent hemp on Jupiter mistake by assuming Type 3 civilizations must use massive radio transmitters.
So, are we falling into the same trap by demanding they use radio waves and Dyson spheres? Shouldn't a Type 3 have technology that just appears magical to us?
That is the right question. However, the sources argue there's a crucial difference between Huygens' time and our own. In the 17th century, the fundamental laws of nature were largely unknown. Today, we believe that the fundamental laws of physics, at the microscopic, atomic, and nuclear levels, are largely known and universal. We aren't expecting a discovery that allows instantaneous teleportation or communication faster than light.
The fundamental rules of the cosmos are established, but the scale of application is not.
Exactly. The knowledge of fundamental laws doesn't follow an exponential growth curve anymore. But what does follow an exponential growth curve are the parameters of the practical activity of civilization. The speed, the complexity of the systems we study, and the scale of technology. And since we think we know the governing laws of the cosmos, we're justified in extrapolating the scale of practical application, the Kardashev scale. Therefore, if cosmic-scale intelligence existed and operated within those universal laws, we should be able to see its manifestation on the scale of 10 to the 44 ergs per second.
And this leads us to the final necessary conclusion on isolation, weighing all the scientific evidence.
The currently observable, law-abiding universe, operating under the physical laws we understand, currently excludes the existence of cosmic-scale intelligence manifesting itself in a detectable way. We've shown that our observational technology is already sufficient to have discovered its presence if it were operating on the expected scales of the Kardashev model. The silence is meaningful.
This conclusion, the possibility of practical isolation, even if it's not absolute, holds immense moral and ethical significance. It fundamentally changes our place and our responsibility in the universe.
It dramatically raises the stakes for humanity. First, the value of our technological and, perhaps more importantly, our humanistic achievements grows immeasurably. We're no longer simply one of billions of evolving species. We become the sole custodians of advanced thought and complex culture in a vast, silent area of space.
And that shift in perspective means our responsibility is magnified. If we are rare, if we are special, we have an unprecedented duty to ensure our own survival and success.
The knowledge that we are the avant-garde of matter, the current peak of organized complexity in a huge part of the universe, this has to serve as an unparalleled creative stimulus for humanity. It makes the unacceptability of barbaric wars, of self-destruction, of environmental ruin just blindingly clear. We cannot afford the self-destruction that defines Scenario 5.
We have to understand that we must choose our own path and strategy for mastering the cosmos, because the message is clear. No one will give us valuable instructions. We are, for all practical purposes, entirely on our own, and the future of advanced life in this sector depends solely on our decisions, right here on Earth. This has been a deep dive into the monumental expectations set by the Kardashev scale and the harsh reality of astronomical observation. We defined the ultimate technological ambition of Type 2 with its stellar mastery, and Type 3 with its galactic mastery.
We detail the precise altruistic radio signatures Kardashev predicted, that broadband transmission concentrated in the centimeter range, often featuring a highly artificial cutout near the 21-centimeter hydrogen line. And then we demonstrated the striking lack of observational evidence, particularly in our local galactic neighborhood like Andromeda.
The final balance of evidence forces a conclusion leaning toward the concept of practical loneliness, a radical shift from traditional concepts of the multiplicity and ubiquity of inhabited worlds.
Even by the most optimistic estimates that are often floated, that the nearest civilization might be 200 or 300 parsecs away, that region alone contains 10 million stars. That astronomical ratio just starkly demonstrates the profound rarity of intelligent life that achieves cosmic manifestation. The universe is huge, and its intelligent pockets are far, far apart.
And this leaves us with a final provocative thought for you to consider, tying back to that concept of cybernetic profitability.
If advanced civilizations ultimately conclude that increasing physical volume or expansive colonization is cybernetically unprofitable, because it slows down the speed of information exchange across the civilization, and they choose instead to pursue the Golden Age strategy of ultimate internal focus and cybernetic compactness, maximizing information density instead of physical presence. Does this suggest that the ultimate measure of civilization success is achieving a state of non-observable, perfect self-containment? And if that is the case, if they've achieved cosmic mastery by becoming functionally invisible, how would we ever know they existed even with a 10 billion light-year telescope?